Hello and welcome to the webinar. My name is Josh McDaniel and I work with the Wildland Fire Lessons Learned Center. I'll be introducing the speaker today and also moderating the question and answer session. But as always, I want to point out that this is a regular webinar series and there's 3 organizations that sponsor it: the Joint Fire Science Program, the Wildland Fire Lessons Learned Center, and the International Association of Wildland Fire. Okay, today's webinar is part of a series looking at smoke science. For the next couple months, we'll be hosting these webinars for the next month or two, actually. There's about 3 or 4 more left. And these were all presentations from projects that were funded under the Joint Fire Science Program Smoke Science Plan. As you're aware, I'm sure you're aware, smoke and smoke management will likely increase in priority in coming years due to a combination of air quality regulations, increasing urban interface, and potential climate change impacts. GFSP research is helping to validate smoke models and projections, improve understanding of smoke emissions, dispersion, and chemistry, increase understanding of human health issues related to smoke, and also look at community tolerance for smoke, as well as climate change. So today, Talat Odman is going to be talking about smoke impact predictions, but there are other webinars on the schedule as well. And here's some of the ones that are coming up. So on March 19th, Don McKenzie is going to be talking about smoke and climate change. On March 20th, there's a webinar that's not part of the smoke series, but is also interesting. It's this isn't the official title. We haven't developed a title yet. Still looking to lock that down. But it's going to be a presentation on heat illness and rhabdomyolysis. This has become an issue that with some accidents and some fatalities related to this over the last couple of years in wildland fire management. So there's going to be a panel discussion of medical professionals, crew leaders, and also crew members who've had experience with this. And that should be very interesting. And that's going to be on March 20th. On May 7th, the smoke webinars will continue with Warren Heilman speaking on predicting local smoke dispersion during intense wildland fires. And then there's a couple more. We haven't quite got the registration set up and the titles and descriptions set up yet, so we haven't got them up here yet, but there's a few more in the works. And if you want to register for those, you can register on the Advances in Fire Practice page, which is part of the Wildland Fire Lessons Learned Center. As you can see right there in this section here, it lists all of the webinars with links to register if you're not already receiving emails with the announcements. Okay. Also, just want to point out that in terms of question and answers, you can type in your questions in the questions box on your control panel to the right, and at the end we'll have a Q&A session, and we'll read through the questions, and Talat will respond. So I encourage you to get your questions in early. The farther up the queue, the better chance we have of getting to it. And also, we're recording the webinar, and we'll post the recording of the webinar on this same page right here, where the webinars are listed, and that the webinars are recorded and archived on YouTube, and they're there for eternity, or as long as YouTube lasts, and you can pass on the link to whoever you think might be interested in that webinar. So on to today. So I now want to introduce Dr. Talat Odman. Dr. Odman is a principal research engineer at Georgia Tech. His research has been in the areas of atmospheric chemistry, air pollution meteorology, air quality, and its modeling. Since 2007, he has focused on wildland fires and their air quality impacts. He has recently completed 2 JFSP projects on sensitivity analyses of emissions and meteorological inputs in smoke models. And with that, I will hand it over to Talat.
Good afternoon. I'm assuming you're seeing my slides now.
Yep, it looks good.
I want to start by acknowledging my sponsors. The work that I'm going to present this afternoon is the product of 2 Joint Fire Science Program projects. I was the PI on the first one, whose name starts with evaluation of smoke models, along with Scott Goodrick of the U.S. Forest Service. And the second project was actually a student project by my student Fernando Garcia, who is now a postdoctoral associate at MIT. I'll also be presenting material from a project I completed for the Strategic Environmental Research and Development Program, as well as an ongoing project with the NASA Applied Air Quality Sciences team. And I want to thank a number of people whose contributions I will present today. First of all, my students, Aika and Fernando, my associate, Yong Tao from Georgia Tech, Scott Goodwig, Young Lu, Gary Achtemeier from the Forest Service, Robbie Greenwald of Emory University, Brian Gullett of EPA, Roger Atmar of Forest Service, and Bob Jokelson of University of Montana. I'm assuming that everyone is familiar with the adverse impacts of wildland smoke from wildland fires, primarily on visibility and also on public health. Now, what I want to focus on today is that we have models for simulating the impact of wildland fire emissions. However, these models are not perfect. There are many uncertainties in their formulations because atmospheric processes involved are complex, and also there are uncertainties in the inputs that these models use. Now, when it comes to decision making, it would be good to know what the uncertainty in the predictions of the models are. But unfortunately, this is an area where we are lacking research and information. And primarily this is because it's difficult to quantify the uncertainty in the models. And I'm not claiming that I'm going to be able to do that today. I will simply show you 3 cases where I'll quantify the uncertainties, and you can get an idea of their possible magnitudes. And also, emission estimates and meteorological parameters are 2 major categories of smoke model inputs. So we're going to take a look at those. So in the first case study, I will look at the uncertainties in bottom-up emission calculations. In the second one, I'll be comparing emission estimates from this bottom-up calculation procedure to the estimates from a satellite. And in the third case, I will be looking at the sensitivities of both emissions and also meteorological parameters, such as wind speed and wind direction, to the predicted smoke, downwind smoke concentrations. Now, the goal of these analyses will be to better understand the leading factors of uncertainty in smoke modeling and point out where the efforts should be concentrated for uncertainty reduction. The first case is the burn at Eglin Air Force Base that was conducted on February 8, 2011. It was a rather large fire, 250 acres of long-lived pine or turkey oak. It was about a 2-year rough, and ignition was performed by a helicopter. It took about 2 hours, and the burn completed in about 2.5 hours. Now, this was part of the RX Cadre study at Eglin Air Force Base during February 2011. And Roger Atmar conducted the fuel study, measured the fuels for this burn. And Brian Gullett measured emissions with an instrument set attached to a tethered balloon. Winds were measured both on the ground and on that tethered balloon. Young Liu measured the plume height with his LiDAR celiometer, and Robbie Greenwald measured downwind smoke concentrations. Now, we're going to start with the fuel load. So Roger Otmar clipped about 20 plots in 3 different locations and sorted the fuels according to FCCS components, and oven dried them and weighted. Now, in this chart, you're looking at the comparison of those measured fuels to the estimates obtained from a photo series. And the specific photo series that was used here is Sand Hill 10 in longleaf pine scrub oak cover type of Rogers photo series dated 2003. So the blue is the photo series here, and for each fuel type we are comparing what we have estimated from the photo series to the field measurements. Now let me just point to the total here. Using the photo series, we have overestimated the fuel load by about 11%. Next, fuel consumption. The same fuel sampling was conducted after the burn, and as far as the modeling is concerned, we have used Consume 3.0, and in this chart you are looking at a comparison of Consume in green to the field measurements for woody, shrub, non-woody, and litter vegetation types. And if you look at the totals, Consume overestimated the total fuel consumption by 15%. Now moving on to emission factors, here we're going to pick values from the literature and compare them to the measurements with the tethered balloon. Now the literature average, and the sources are listed here, AP42, Urbanski et al., who listed 2 different emission factors for the Eglin Air Force Base. And this is from the same tethered balloon, but for different burn units at the Eglin Air Force Base. So we collected those numbers, and the average, or the mean I should say, is 13 grams per kilogram with an uncertainty or standard deviation of 3.4. Now the measurement for this particular burn was 14, and there is also an uncertainty in this measurement. Now, how are we going to estimate the uncertainty? Emissions are calculated by taking the product of fuel consumption and emission factors. So we're going to calculate the uncertainty in emissions as a combination of fuel consumption and emission factor uncertainties. Now, as I mentioned before, there is an uncertainty in the measurements, so we're going to take the standard deviation of the measurements. For example, all the different plots that were clipped lead to a mean as well as a standard deviation. As far as the model uncertainties are concerned, we're going to look at the differences between the model and the measurements. There are other sources of uncertainties, but we're trying to reduce them as much as we can by adjusting model winds, for example, with the measured winds. And we're going to propagate those uncertainties in our dispersion model and come up with the uncertainty in predicted downwind smoke concentrations. and then we'll finally compare the model concentrations to the measured downwind smoke concentrations. This is simply showing how we measured the winds, and the original modeled winds, represented with these purple dots, were adjusted with the measurements that we had both on the ground and also on that tethered balloon. And this was done both for wind speed and wind direction. Now the models, and these are models that I'm going to use throughout the three cases. For meteorology, we're going to use the weather research and forecasting model known as WRF. The dispersion part, and with dispersion I'm referring to the small-scale short-range phenomena of smoke dispersion. We're going to use a model called day smoke, which was developed by Gary Achtemeier. This is an empirical dispersion model specifically developed for fire plumes. And the transport model is going to be the community multi-scale air quality model known as CMAQ. So this is the model we're going to use for larger scale, long-range transport. It has chemistry in it, and the fire plume is injected into the CMAQ grid, where it's going to mix with emissions from all other sources. Now here are snapshots of the modeled fire plume from day smoke. Now, these are the measurement sites. We had a stationary site as well as a mobile site. It's essentially a truck with instruments. And in this slide, let me spend some time to explain what everything is. So there are two lines. The purple line is the result from day smoke using the measured emissions. So we have a time axis here, and this is at the stationary site where we have two instruments measuring PM2.5 concentrations, a TEOM, which is considered to be a more accurate instrument, as well as a handheld instrument, AeroTrack. So those diamonds are showing the measurements. Now the orange line is also a day smoke prediction, but that one is using the model emissions as an input. Now, and these lines are actually the mean coming from the day smoke. Day smoke is a stochastic model which gives you a range. So these black lines are showing the range of the uncertainty that day smoke models and associates with atmospheric turbulence. Now, there is also a purple band which is showing the uncertainty associated with the uncertainty in measurements. So this is what we have taken as the uncertainty in measurements and propagated into day smoke. And then the green band is showing the uncertainty that is coming from modeling the emissions. And the bottom panel is showing the same thing essentially at the stationary, the mobile site, which was more distant, which was about 9 kilometers downwind. The stationary site was about 3 kilometers downwind. So One of the problems that we had in this case, if you notice, these measurement sites, the stationary and the mobile sites, are kind of to the edge of the model plume. And that is also what happened in reality. Our crews reported that the smoke was weaving to their left, further towards the west, because the predicted winds were northerly, but then they shifted to northeasterly. And unfortunately, the stationary site you can't move anyway. The mobile site was restricted with the road network as well as some target practice by aircraft to the west of the burn unit, so they were not allowed to move any further to the west. So one would, of course, prefer that the measurements are along the center of the plume, but that wasn't possible. However, you know, we can model the plume everywhere, and we can also quantify the uncertainty. And in this case, we have looked at the uncertainty along this arc, which is about 9 kilometers downwind from the burn site here. And what we observe is that both the concentrations, downwind smoke concentrations, as well as the uncertainties are growing as we move. This is where our mobile site is, as we move from the edge of the plume to the center. So we can expect higher uncertainty at the center of the plume. But when we look at the model uncertainty due to turbulence, then we see an interesting feature. Towards the edges of the plume, that uncertainty was approximately equal to the uncertainty from modeling the emissions. And as we move towards the center of the plume, we see that the uncertainty associated with modeling the emissions is larger than the uncertainty due to turbulence. All right, so a brief summary of what we have seen. On average, measured the uncertainty in measured emissions was 18%. And when we propagated it in the day smoke dispersion model, that translated to a 20% uncertainty in downwind concentrations. Uncertainty in modeled emissions was about twice that of measured emissions, 36%. And it's resulted in 42% uncertainty in predicted downwind concentrations. And uncertainties increase towards the center of the plume, and the uncertainty due to emission inputs is larger than the uncertainty attributed to turbulence. Now our second case is going to be a comparison of bottom-up estimated emissions to satellite-based emission estimates. And the case is Williams Fire that occurred on November 17, 2009 near Bullton, California. This is north of Los Angeles. 200 acres of coastal sage shrub, better known as chaparral, was burned. So bottom-up emissions, it's essentially the same method that we used in case 1, except, of course, we were using a different photo series. So this is what we have found, best matching the fuels on the ground. So we estimated about 8.1 tons per acre for shrubs and 9.2 tons per acre for litter. Consumption, again, we're using consume. Now FEPS is for the to get the time rate of emissions. That's the model that we use, fuel emission production simulator. And the emission factor that we are using is 8.6 grams per kilogram. And these are the sources where we get those numbers. Now the satellite-based estimate is coming from the global biomass burning emission product that can be accessed at this website. These are pictures from the GO satellite, and if you can focus in this area, you can actually see the smoke plume associated with this burn. Now here's the comparison. The total for bottom-up emissions was more than twice that for the satellite-based estimate. So the bottom-up for different hours, these are the hours, so it's about a 4.5-hour burn. The bottom-up emissions are shown by purple bars, satellite by the blue bars. Now notice that the bottom-up emissions are almost constant for the 4 hours of ignition. So we are assuming in the model, in this 5 emission production simulator, uniform spread of the fire, but the satellite is showing a trend, that is increasing, that starts small and increasing towards the middle of the fire and then tapers off. So what we did, we thought that that may be a more realistic distribution of the 5 emissions, and we took that time profile and applied it to the bottom-up estimate. So those are the green bars. So the total of the green bars is the same as the total of the purple bars, but it has the time distribution that we got from the satellite. So we're going to call that third estimate bottom-up FER. Now there was an aircraft sampling the plume throughout this burn, and it measured light scattering that can be converted to PM25 concentrations. Let's call it smoke concentrations. And it also measured wind speed and direction. And there's this portion of the flight shown with the blue line where the aircraft was doing traverses in the smoke plume, so we're going to focus in that portion. So this is what happens when we use the bottom-up emissions estimate. So here is a top view of the smoke that we simulated, and the aircraft path is shown here along with the concentrations that the aircraft has measured. And on the right-hand side, this is the side view of the same plume. So the aircraft is up here, the smoke, the plume center is somewhere down here. So we can say that with these emissions at this time, the plume height is a little bit underestimated. The plume is not as high as where the aircraft found it in reality. And this is what happens when we use the satellite-based emission estimates. Again, the top view and the side view. Now this time, the plume height is way underestimated. The center of the plume is somewhere down here. The aircraft is finding the plume up there. And this is the bottom-up FER. So the bottom-up emissions redistributed using the satellite emission rate profile. So that happens to be just right. That puts the plume at this time the plume center is right along the aircraft track. So now now let's compare what the aircraft measured to the modeled PM2.5 concentrations. So this arrow is where is pointing to the measurement at this position of the aircraft, and the aircraft is going to follow this track. And this is how it looks in the vertical. So it's traveling at about 1,200 meters altitude. So at each traverse, the observations shown in red are showing it peaking in PM2.5 concentrations, and then the bottom-up emissions, the model using bottom-up emissions estimate is also showing some peaks, but notice that they are way lower than what the aircraft is measuring. Satellites, similarly, it's even lower. The peaks that we model are lower, but look at the green line, which is the modeled concentrations with the bottom-up FER emissions estimate. So those seem to be just right when compared to the peaks measured by the aircraft. And here are some statistics, mean bias. Notice that bottom-up FER mean bias decreases sharply compared to the other two estimates. The error is also much smaller. So in summary, aircraft measurements can be used for evaluation of emission estimates, but you have to go through dispersion modeling. Now, one of the difficulties here compared to the previous case where we were using ground-based measurements is that with the aircraft is moving constantly. So the averaging times, it's not like averaging for a stationary monitor. The aircraft is moving constantly, so you have to use a very short averaging time step, like something like 20 seconds. And inherently, there are going to be turbulent effects that you're going to start capturing when you average for such a short amount of time. So the measurements will contain uncertainties, perhaps larger uncertainties than what you would get at the ground. For this case, the satellite is clearly underestimating the emissions, and the adjustment of bottom-up emissions with satellite-derived time rates were beneficial in this case. All right, the third and final case, this is going to be the Atlanta smoke event that happened on February 20, 2007. Two burns totaling about 300 acres were started on that morning when the winds were northeasterly, but then they shifted to southeasterly. And these burns, one was at the Piedmont National Wildlife Refuge, and the other one was at the Oconee National Forest, both about 80 kilometers southeast of Atlanta. So when the winds shifted, the smoke was carried to Atlanta, and this is a clip from the next day's newspaper. This was big news. The concentrations at several Atlanta monitors reached 150 micrograms per cubic meter. All right, so we did the initial modeling for this. Now, since this is going to be 80-kilometer range, we're going to transfer the dispersed plume to the CMAC model, and and there are also other sources of PM2.5 between where the fires were in Atlanta, so we need to take those into account. So we're going to hand over the fire emissions to the CMAQ model, where all those emissions will mix, chemically react, and the winds will transport the fire plume to Atlanta. So these are the fire emissions that we predicted for the Oconee and Piedmont burns. Now, both burns had about the same acreage, but the fuel loads at Oconee were much larger because it was an older rough. Now, when we use those emissions in the CMAQ model, this is what we got, the blue line. And the yellow dots are the observations. Now notice that they go up to about 140 micrograms per cubic meter at this site, the South DeKalb site, which is in downtown Atlanta. What the CMAQ model predicted at that peak time was only 60 micrograms per cubic meter. Now we're clearly underestimating the fire impacts. So to understand the reason for this underprediction, we conducted several sensitivity analyses. We changed the grid resolution in the CMAQ model. Then we perturbed the magnitude of the emissions. We looked at the plume height versus the planetary boundary layer height. We looked at the temporal time rate of the emissions. And we also looked at wind speed and wind direction. And part of this work, at least the sensitivity to the wind fields, was published just recently. Now for grid resolution, we have developed an adaptive grid version of the CMAQ model. So this version allows us to decrease the grid resolution where the fire plume is. And in our original simulation, the grid resolution was 4 kilometers. With this adaptive grid version, we're able to reduce the grid resolution down to 100 meters near the source of the fire. And what that gave us was an improved simulation shown with the green line here. So the peak was increased, but at a later time. And also I should point out here that when we use the 4 kilometer resolution, these two burns resulted in a single plume. And the two burns and their distinct plumes were resolved when we used the finer resolution. So just because of that, I mean, you can expect a more accurate prediction from the adaptive grid model. And that's what you get. South DeKalb site, I believe, is perhaps this white dot here. So right there, we're getting an improved smoke prediction. But still, there is a gap, between the model and the observations. So what we did, we increased the magnitude of emissions until the model predictions matched the observations, and we were able to achieve that when we increased the emissions by a factor of 4 to 6. Now, recall the uncertainties that we have seen for cases 1 and 2. This kind of uncertainty in emissions is not realistic. I mean, we cannot say the emissions were underpredicted by a factor of 4 or 6. So we looked at other things. One of them was the vertical allocation of 5 emissions. Most of the 5 emissions went into layer 10, model layer 10, which is at about 1,000 meters above ground. Over here, this dashed line is showing the boundary layer height. Now let's take a look at layer 10, which is this purple line here. So that's the top of layer 10. And this is the bottom. The green line is the bottom of layer 10. So notice that until this time, the PBL is below layer 10. So the emissions are actually going above the planetary boundary layer. They're not mixing to the ground. And this is what we see here when we look at different layers, the contribution of emissions that went into different layers. When we look at layer 10, its contribution is very small until about 1800 UTC. I switched the time on you, unfortunately. So if you subtract about 5, you'll get to the Eastern Standard Time. So until about 1800, the PBL was below layer 10, so all the emissions went above the PBL, and they had no impact on the PM, downwind PM concentrations. But then after that time, once they get into the PBL, then they start having an impact. All right, we also show that there was a sensitivity to how you allocate these emissions in time. Now, again, this is the time pattern of the emissions. And these are the sensitivities, or the contributions, I should say, of emissions at different times. Emissions at 1300. $1,400 in blue, and then 1,500. So when you see this peak concentration, that is when there is a larger contribution from emissions from the later hours of the burn. We also looked at the sensitivity of wind direction. Now, we did that by simply rotating all the winds. Now, the winds are not uniform. The winds are predicted by the WRF model, but we're going to take and rotate all of the winds by a certain amount. And this is what we got. This is the result that we got for different angles of rotation. Especially for a -5-degree rotation, we did see a large increase in predicted concentrations at this site. We also looked at the sensitivity to wind speed, and again, we uniformly increased or decreased the wind speed over the entire domain at all times. And we did see that when we decrease the wind speed by about 30%, we do see a large increase in predicted downwind smoke concentrations. Now, these are the comparison of the modeled winds to the Peachtree City sounding. The top panel is showing all the way up to 20,000 meters, we of course are interested in the lower portion where the smoke plume is transported. So when we zoom into that first 2,000 meters, we do see actually a fairly big difference between the modeled wind speed, which is in red here, and the measured winds. So the winds were approximately overestimated by 30%. So based on that, we did a final modeling. We did increase emissions by about 15%. That's roughly the uncertainty that we got from the first two cases. We skewed the emissions towards the end of the burn, and we made sure that the plume is in the PBL at the end of the burn. We reduced the wind speed by 30%, and that is what we got by reducing the wind speed by 30%. Now, the wind, changing the wind direction helped. That is the one. But when it was combined with the wind speed, it wasn't beneficial, so we removed that. We just used the original wind directions. And, you know, we did see improvements at pretty much all downtown stations in Atlanta. All right, so in summary, accurate modeling of 5 impacts with regional scale air quality models depends on fine grid resolution and accurate emissions and meteorology inputs. Downwind smoke concentrations are sensitive to the fraction of emissions that go into the planetary boundary layer. Reducing uncertainty in the temporal distribution of 5 emissions can improve accuracy. Sensitivities to wind speed and wind direction are large, especially within the range of uncertainties in numerical weather prediction models. In this case, those sensitivities were larger than anything else that we looked at. So the meteorological uncertainties may largely account for the differences between downwind smoke observations and predictions. And that may be an area where we should focus on if we want to improve the accuracy of the smoke impact predictions. So with that, let me stop and take some questions.
Okay, thank you, Talat. I appreciate that. That was very interesting. Let's see. Let me get to the questions here.
And by the way, this is Aika and Fernando, my students, at a burn at Fort Benning about 5 years ago.
Okay. So far, we only have one question. So if anyone else out there has some questions, go ahead and get those in, and we'll get to them. Trevor Miller wants to know if you could touch on a little bit more explain a little bit more measured emissions versus modeled emissions. Talat, could you hear me?
Okay, yes, I can hear you.
Okay.
I guess what I can say is this. At that Eglin burn that I showed you, we were at the site with a tethered balloon measuring the emissions. You're not going to be able to do that all the time. In many cases, you have to use models. For example, you have to use photo series to estimate fuel loads. You have to use a model like Consume to estimate fuel consumption, and you have to rely on emission factors for similar types of fuels. So all those things combined, is what I call a modeled emission. And of course, the uncertainties in that is going to be larger than, what you actually measure at the site. But that is not to say that the measurements are 100% accurate. There are also uncertainties in the measurements because the balloon is not sampling over the entire plume. It's only flying at certain points in the plume. I don't know if I could answer the question.
Okay. So Trevor, write us back if that still hasn't quite got it. Maybe ask something a little more specific, and we'll see if we can get Talat to answer that. Tom Moore asks, any thoughts on the effects of the instantaneous dispersion of the fire emissions to the full grid cell dimension in the PGM?
Yes, and that happens. I mean, we try to model a plume with a dispersion model like day smoke in great detail, and then we take that and inject it into a grid-based model like CMAC, and at that moment, it's instantaneously mixed into the grid cell, which is a source of inaccuracy itself. And I touched on that with my sensitivity on grid resolution. So when we used 4-kilometer grid resolution, for instance, was more of an issue. But when we went down to 100-meter grid resolution with the adaptive grid model, we reduced that uncertainty.
Okay. Next question is from Martin Stouffer. He says, I wonder if you thought about using the WRF chem biomass burn emission model that is included and inline coupled to the WRF and WRF chem model. The plume rise model is included too and showed good results in Alaska. A model comparison would be nice with your great set of observational data.
So this is the WRF S-fire model, I believe, that is being referred to. Yes, I am aware of that model. That actually is one step ahead of what I'm doing. It's a model that takes into account the interaction between a buoyant plume and the local meteorology. So the plume, the hot plume, as it rises, it's going to affect the local wind fields. So that model, couples the fire with meteorology. In the modeling that I've shown you, I'm simply using WRF, and the wind field, the wind field is the most important meteorological parameter here, but that has no knowledge that there is a fire going on in our simulations. So yes, I agree. A model like WRF, S-fire, is a much more advanced, approach, and it should be compared to what I'm doing.
Okay. Willie Bagey writes, would the future use of drones be practical for research and refining smoke modeling programs?
Well, at one of the RX Cadre burns, I believe, even for the burn, that I showed here, there were drones. They were mostly used to videotape the burn to look at the fire spread and so on. But one of them had an anemometer attached to it, and it did measure winds. And we had access to that data. Now we weren't able to use it, but I believe with proper design and so on, drones could be very useful. And in fact, I now remember another drone had a atolometer that measured black carbon. So it's conceivable that as the instruments get smaller and the payloads of the drones increase, we can attach instrumentation that would be very useful in order to study fire plumes.
Okay. Yeah, that gives me a chance to make a short plug for the Advances in Fire Practice on the Lessons Learned Center site. We're going to be posting an article this afternoon or tomorrow, should be shortly, on the use of drones on the last year's rim fire in California. And there was a collaboration between CAL FIRE and the California National Guard and using a drone for perimeter detection and using the infrared cameras for spotting, detection of spot fires, that sort of thing. So something that's probably coming in the very near future to fire management and probably fire research as well. Okay, the next question is from Carsten Bauman. Does the chemistry module in CMAQ take into account SOA formation? How does SOA contribute to PM2.5 downwind, and what is the uncertainty of this contribution?
Yeah, that is that is an area that as you know, is new focus of the Joint Fire Science Program. Yes, we did experience SOA formation, especially in the Atlanta smoke event, the third case that I showed, and we have a joint paper with Carsten where we do show significant SOA formation. Now the model that we used is lacking in forming SOA. It is forming it, but it's not to the level that was observed. So most of the PM predictions were primary.
Okay.
And yeah, that's another source of uncertainty. But you do get SOA formation in some burns, you don't get it in other burns, so we really need to increase our understanding of SOA formation in fire plumes before we can model it properly.
Okay. James Brenner writes, the statement emissions has been used in this presentation repeatedly, and we assume this refers to PM 2.5. Were other emissions also measured or modeled?
Well, they were measured and modeled, but I did focus on PM 2.5 in this presentation. I did not specifically state it, but it was mostly marked as PM 2.5 in my slides. Now, why PM 2.5? When modeling is done, typically all other emissions are related to PM 2.5 emissions. There are some ratios, fixed ratios between, say, PM 2.5 and CO emissions and other species, VOC species, for example. But everything was included, as much as we can model, was included in the models, and conversions to PM2.5, as far as their model, they're also included in predicted PM2.5 concentrations, but as I said, SOA formation is lacking. So, most of it was primary PM2.5, emitted as PM2.5.
Okay. Douglas Fox asks, most of the applications of regional modeling with chemistry are looking at impacts of multiple sources over hourly to daily periods to distinguish the significance of the fire emissions. How would you describe the significance of your findings for this type of application?
I'm reading the question more carefully here in just one moment. I wonder if he is speaking of multiple sources other than fires. Yeah, I mean, these prescribed burns that I studied, these 3 cases, they had an impact that didn't last more than a day. I mean, the next day, the smoke emissions were out of the Atlanta domain, for example, and everything was back to normal. And measured concentrations dropped to the normal levels. But when you have a case like wildfire that goes on for multiple days, then you have to, I guess, model for longer periods. But I would appreciate a more specific question.
All right. So Doug, maybe if you can specify a little bit more what you're asking there. We'll move on to the next one. In the meantime, John Waldrop asked, do you have any opinion on the concentration accuracy of most smoke models once smoke is airborne and the time from fire ignition increases? For instance, a burn is conducted at noon and the smoke production is low by evening. However, the smoke is still in the air and begins to descend as the night cools.
Yeah, I mean, nighttime is a whole different ball game. I mean, the model that I'm using here, as the name suggests, day smoke, is looking at daytime smoke. Nighttime is much more difficult, more challenging. We're looking at PVL heights of 500 to 800, even 1,000 meters here. The nighttime is going to become more challenging. That's all I can say.
Okay. Well, I think that's all the questions we have right now. So, Talat, I want to thank you. That was a very comprehensive and very interesting presentation, and we look forward to hearing more about this.
Well, I thank you for the opportunity.
And for everyone else out there, if you, I will post a link to the recording of the webinar on the Advances in Fire Practice page. Again, you can find that on the Lessons Learned Center site. If you go under the Resources tab, and you can pass that along to anyone you need. And we look forward to having you here for the next webinar. Thanks a lot, and thanks everyone else out there.